Hello, physics. This is the third part of the chapter 6 and 7 slides. So let's jump right into it. Do now. First of all, what is F sub g? Well, F sub g is weight, and the formula for F sub g is mg. Second question: what are the four-step of Dr. File's four-step strategy for force problems TM? Well, again, mine is a six-step four-step strategy because I always start with step huh and finish with step hmm. So I would do step huh, and then step one would be sketch. Step two would be free body diagram. Step three would be Newton's second law, F equals ma, but really sigma F equals ma, where F and A are wearing hats. And then step four is math. And then step, think about your answer at the end. So third question, what is the only thing we attach to the box in step two, the free body diagram? The only thing you attach to the free body diagram are forces, only forces. Question four, is acceleration a force? No, acceleration is not a force. Acceleration is acceleration. Force is force. So acceleration has units of meters per second squared. Force, F, has units of newtons. So acceleration is not a force, and by the same token, mass is not a force. Mass has units of kilograms. Fifth question, is velocity an acceleration? No, it is not. Velocity is meters per second. Acceleration is meters per second squared. They're related, but they're not the same thing. So be on the lookout for that. 6, what's a milliner? A milliner is a hat maker, or sometimes a hat salesman. Like an old department store might have a millinery section. It's hats, is what that is. Seventh question, why would a milliner care about step 3? Because step 3, Newton's second law, F equals ma, is really sigma F with a hat equals ma with a hat. It's all about the hats. Question 8, what's the first part of step 4? Step 4 is math. The first part of doing math in a force problem is taking the hats off and putting in the signs. So keep that in mind. And 9, what's a red herring? A red herring is a false clue. It is something there to distract you. So be on the lookout for red herrings in your physics problems. You will often get some information that when you first see it, seems like, oh, I'm definitely going to be using this number somewhere because it's important. But once you get to doing the problem, you'll see that that piece of information is just there to distract you. You have to ignore it. So friction, when have you experienced friction? Pretty much all the time, always. It's always something that's going on. So if you play a stringed instrument like this, where you're drawing the bow across the strings, it's friction between the bow and the strings that makes the strings vibrate, which leads to the sound. If you're dancing, or if you just wear shoes or touch the ground with your feet some other way, well, yeah, there's going to be friction between your feet and the ground. Tennis, any kind of sports, especially tennis on clay, the player runs to the side, slams on the brakes, and then slides a great distance to get to the ball. And the tennis player has to take all of that into account. There's definitely friction going on there. And this sport over here, curling. So the guy throws the stone or the rock, whatever it's called. I think it's called a stone, down the long lane towards some target that we can't see in this picture. And his teammates are here with brooms, smoothing out the ice, making this thing go, a little bit straighter. They can do one side more than the other to make it turn, things like that. They're trying to control how far this thing's going to go by controlling how much friction it's going to experience. So yeah, there's friction all over the place. So friction is a force. So when two solid objects come into contact with each other, the friction is due to surface irregularities. So what that means is even if you have two things that are smooth, at least when you're looking at them with your unaided eye and they look very smooth, if you were to zoom way in, like this picture is doing here, so maybe the bottom of the crate looks smooth and the surface, the concrete surface it's on, also looks smooth. If you could zoom in microscopically, you would see they're actually very irregular surfaces. And as they're moving past each other, things are bumping against other things. So in Physics 1 in high school, this is what we say friction is due to. This is true. This is totally, totally true, but it's not the whole truth. There's more going on. There's all kinds of different things happening at the molecular level and different types of chemical bonds being formed and broken and things like that. So it does get very messy. There's more to the story than this. But at this level, this is how we learn friction. We say that friction is due to surface irregularities. If you decide to major in physics and go into material science and things like that, you can learn the more sophisticated aspects of this. But for now, friction is due to surface irregularities. So we're going to deal with two types of friction. Kinetic friction, this is when the surfaces are moving relative to each other. So if you slide your hands back and forth against each other to warm them up, well, it's friction going on that's warming them up. So for example, another example, if you're pushing the sofa across the room successfully, meaning the sofa is moving, you're fighting against kinetic friction. The bottom of the sofa is moving relative to the surface of the floor. So you're dealing with kinetic friction because the two surfaces are moving. Static friction occurs when the surfaces are not moving relative to each other. So static friction, if you're trying to push the sofa but it's not moving because there's just too much friction, well, that is friction that's keeping you from moving it. It's still a force that's going on. But if the surfaces are not moving, we call it a different name. We call it static friction instead of kinetic friction. So we will deal mostly with kinetic friction. So if you're looking at the formula here for kinetic friction, you will see that it will depend on two different things. The first thing is the kinds of materials involved. So there's two surfaces that are in contact with each other. What exactly those surfaces are, it's going to affect how much friction you get. And the other thing, so the two over here, is how hard the surfaces are pushing against each other. So that's the normal force. Two surfaces are in contact. There's a normal force between them. Of the two factors, that's kind of the more readily apparent one. If the things are pressing together more, you're getting more friction. The other thing, this guy here, the kinds of materials involved, this is handled by something called the coefficient of kinetic friction. And the symbol for this is mu sub k. So mu, it looks like a funny U with an extra stick on it. It's the lowercase Greek letter for m, mu. It is spelled mu, and it is pronounced mu. So that is mu. Capital mu is just a capital M. Lowercase mu is this funny looking U-shaped thing. Or it also looks like an H that you flipped upside down, kind of. It's a thing. So yeah, here is your formula for kinetic friction. F sub k is equal to mu sub k times F sub n. So if we compare them, the formulas for kinetic friction and static friction, they look very similar. For static friction, it's F sub s, and on the right side, you have mu sub s times F sub n. The big difference is in between them, instead of having an equal sign, you have a less than or equal sign. Static friction is weird, and I don't want to, we'll talk about it every once in a while. I don't want to go too far into it here because we're mostly dealing with kinetic friction. But yeah, static friction works a little bit differently. In both cases, however, the friction opposes the motion. So if your thing is actually moving to the right, well, then your force of kinetic friction will be moving to the left. If you're instead, the thing is not moving, you're pushing on the couch, but it's too heavy, there's too much friction, it's not moving. If you're pushing to the right, static friction is opposing the motion you're trying to put on it. So that would be going to the left. So whether the object is moving or trying to move, the friction will oppose the motion. So this table here shows a bunch of different combinations of materials. It's always two things together, steel on steel, aluminum on steel. In this first column, the middle column is mu sub s, the coefficient of static friction, and the rightmost column is mu sub k, the coefficient of kinetic friction. So when you're looking at these numbers, you will see they tend to be numbers between 0, I mean greater than 0. A coefficient of friction of 0 would be frictionless. So it's some number greater than 0 and usually less than 1. So if we look, for example, at the first one, steel on steel, let's look at mu sub k. So these are two, pieces of steel moving past each other. The coefficient of friction between them is 0.57. That's a fairly high coefficient of friction. Bare steel on bare steel, there's a lot of friction going on there. So 0.57 in other contexts, that's a fairly low number. But as far as coefficients of friction, it's a fairly high number. So you compare other things. So all the metals on metals, so those are fairly high. Rubber on concrete, dry, 0.8. So that's fairly high. Rubber's a fairly grippy thing on concrete. But notice when the concrete is wet, you have a much lower number for your coefficient of friction. What this means is if you're driving your car and the road is dry, well, your tires are very grippy. And that's good because that keeps your car going in the directions you want it to go in. If, however, the concrete is wet, you've got a problem. You've lost a lot of friction. Your tires have lost a lot of grip. So you've got to drive slower when the road is wet. It doesn't have to be pouring buckets of rain. If the road is just a little bit wet, if it rained, half an hour ago and the road is still wet, your tires don't grip the road nearly as well. So drive carefully. So lots of other things. Teflon on Teflon, well, that has very low coefficients of friction. Teflon is the non-stick stuff. So it's there to, minimize the friction. And finally down to synovial joints and fluids. So in your elbow, in your knee, in your shoulder, in any of the joints, you don't actually have bare bone rubbing against bare bone. At least if you're healthy, if you've got a good healthy joint, that's not what you have. Typically there is synovial fluid between those two bones, and that lets the bones move past each other much easier, so you have less friction and less pain, and your bones don't grind each other down and things like that. So I don't know if anyone's interested in going into a medical field or, doctor, nurse, physical therapy, occupational therapy, things like that. This idea of friction applies there too. And then you see in bold too that for any two surfaces, mu sub s will always be greater than mu sub k. Well, on this table, sometimes it's the same number. If you went out more decimal places, you would find that mu sub s is a little bit bigger than mu sub k. It always takes a little bit more force to break static friction than you experience when you're dealing with kinetic friction. So here's our thing. This slide showing you our new quantity, which is the coefficient of kinetic friction. Its symbol is mu sub k. Its units are none. It doesn't have units. Force has newtons, distance is meters, time is seconds, things like that. Coefficient of friction, whether it's kinetic friction or static friction, it's unitless or dimensionless. It doesn't have any units, which is a little bit weird, but that's how it is. And this thing is a scalar. So we'll do a quick bit of what's called dimensional analysis, which means look at the units of the thing. So here's your formula for kinetic friction. F sub k, the force of kinetic friction, is equal to mu sub k times F sub n. So that is the coefficient of kinetic friction times the normal force. All right, well, the left side of this, F sub k, that's force. That means it has units of newtons. If we look at the right side of this, F sub n, well, that's also a force, so that has units of newtons. It's a rule that whatever newtons you have on the left side, whatever units you have on the left side, you have to have the same units on the right side. So if the left side is in newtons and F sub n is already in newtons, well, that means mu sub k is not allowed to have any units, because if it did have units, it would be changing the units, and we already have the units where they need to be. So again, mu sub k, coefficient of kinetic friction, is dimensionless. It doesn't have units. Often in science, if you see something and it's called a coefficient of something, or sometimes an index of something, that often tells you that that thing doesn't have units. It is a dimensionless number, also called a pure number. So friction, Alice pushes a 200 kilogram piano across the floor. The coefficient of kinetic friction between the piano and the floor is 0.20. And there's some things we would want to figure out. What's the normal force on the piano in part A? And in part B, how hard does Alice need to push to keep the piano moving at a constant velocity of 2.3 meters per second? So I will do a different slide where I'm solving this problem on a Jamboard and showing you how to do this kind of problem. And I will put the link to that problem in the description to this particular video. So I will do that. And that is the end of part 3 of these slides, the chapters 6 and 7 slides. So hopefully you're finding this helpful.